Frank.
Hi, Frank.
Most of you should know me by now, I hope. If not, something's wrong with you. Today I'm going to be talking about robotics control and then an overview of RAS, which everyone here seems to want to know about or learn about, use, etc. To get really in, the reason why I'm having to go to robotics control is because it really leads up into RAS. There's a lot of concepts and there's a lot of concepts in RAS that you kind of need to know for it to make sense. It really is based off of kind of the industrial robotics standard that has been developed over the last however many years, like 40 years, 50 probably. And so to really see what's happening in RAS, I would say you'd have to know robotics from an industrial robotics viewpoint. This is very different from the robotics that you do in RAS mostly. A lot of robotics you do in RAS is simplification, where you don't need to know your robot doesn't need to be aware of its whole situation, right? Rather, you don't, usually if you mount, say, an IR sensor on a robot or a sonar on a robot, you don't tell it how far off like it is from like your drive wheels or anything. You just make this assumption that this number that I'm getting out of my IR sensors is going to mean something, and then I tune these numbers, or I write some code that does things with this number, and that's all you need to output power to the motors. However, in industrial robotics, right, often you consider much more than just this, right? When we talk about a robot, we typically talk about a set of joints and links. Let's consider, it's a good robot to consider, R2-D2. R2-D2 had an arm, right? With some sort of hidden inside of it.
On the sides.
Yeah, something like that.
We're just talking about full distance from the manipulator arm, not a well, I think is what he was going for.
Yeah, something like that. It has eyes now. Okay, so let's imagine some arbitrary robot. An arbitrary robot can be viewed as a list of links and joints. A joint is a joint. Let's say my arm, right? I have a joint here. I'm going to call this a joint. There's a few joint types that we talk about commonly. The two most, no, I guess not. The names of that we use for them are going to be something like revolute, prismatic, continuous. Got the first one should be just fixed. And this is enough. There's other ones where you have more freedom than this, but most you can conceptualize it as just things like this. A fixed joint, we're talking about a connection that's fixed, doesn't move. Revolute spins, right? My elbow here is a revolute joint, in a sense, where as I spin this joint along this axle here into my arm, this portion of my arm rotates. And so here we're going to name our revolute joint. R2-D2 will probably have another one here where his head spins. It rotates along this axis. Prismatic. Prismatic talks about linear motion. Prismatic joint is one that slides. So if you have any kind of rack and pinion setup or a screwdriver or pulleys or something like that, usually you end up with prismatic motion. Continuous is more like your wheels, where it spins and it'll keep spinning. The term link refers to any actual body with mass on the robot. So you have several links on this robot that are joined together by joints. The joints may or may not move by some scheme. This leads us to the term frames, which you see a lot in RAS and in robotics. Everything is talked about in terms of its frame, right? So let's say R2D2. R2D2 probably has some generic root frame that arbitrary root frame that we, if we built R2D2, we would give him some kind of location that we're going to call his origin. I'm going to call it right here between his strap axles. This will be our base frame. RAS, I won't get into RAS yet. That's our base frame. Other frames on him are, for example, the frame of where his wheels are, the frame of how his head is rotated, the frame of this body here. And these frames can change based on what the location of your joints are. There are other frames not a part of R2D2 that he might have to conceptualize, such as world frames, things that aren't attached to him. Right? So there could be a frame somewhere attached to the world, and as his drive wheels move, his base frame moves relative to that world frame. And we use this the term odometry to refer to your robot's position in the world, perceived position in the world relative to some fixed world frame. Another thing that we commonly will have to talk about is different types of motion, what level that we're going to control things at. So when we deal with robotics in RAS, often we deal with things at actuator level, meaning I'm going to set my motor power up to 100%, 80%, something like that. This is what we will refer to as control in actuator space, where we're not actually, we don't know what motion it's actually going to cause. All we know is we're outputting power. However, there is actually some scheme as to where, if our actuator turns a certain amount, we know the diameter of this wheel right on the floor, and if we turn it a certain amount, we know how much this joint here is going to rotate. Or we can perceive that by our encoder or feedback, if we have encoders on the wheels or something like that. And referring to it in terms of its how it's actually, the wheel is actually moving would be in joint space. This is probably better visualized in something like an arm, whereas we talk about however much this joint here has turned is how much, where we talk about how much this joint has turned rather in terms of like how many radians it's turned from some zero reference, as opposed to how much power we've given to it. The one step further from that would be Cartesian space, where we talk about turning this joint, we would move, say, this frame here by a certain amount in Cartesian space. A few vocab words that you'll probably often encounter that may not be obvious. Degree of freedom, things commonly used. These are also commonly used acronyms. You'll see that a lot, degree of freedom. When we refer to something floating in 3D space, we don't actually refer to it as 3 degrees of freedom, it's referred to as 6 degrees of freedom, because you have 1, 2, 3 linear directions that you move in, and then 3 rotational directions also along with that. So you actually have 6 degrees of freedom in 3D space. I can't think of any other vocab words actually that they might need to know.
Effort is perhaps not.
We use the term effort to refer to So depending on what kind of joint you have, if you have a revolute joint, you talk about your moment of inertia across your joint, in the units Newton meter. Whereas if you have a prismatic joint, you talk about in terms of your force, which is in the unit newtons. Although in a robotic system, you commonly don't want to have to consider the two cases separately, kind of, and so you refer to either of these units as your effort, depending on what kind of joint you have. I'm getting a lot of confused looks. If there's any questions at any time, feel free to ask, by the way. Anything else?
Indefector.
Indefector? Actually, looking at the textbook, right, tool frame is used a lot.
Or tool frame.
Yeah, so R2D2 has an arm, right? At the end of the arm, we commonly refer to in a robotic arm, you'll typically have a point at which you're going to control in some way, right? This is commonly referred to as your tool frame. I thought Josh was making stuff up when he wrote this, but it's actually real. And this is the frame of your end effector, which in a lot of concepts in robotics, you're going to try to control the end effector of your robot rather than controlling all these joints and your wheels in order to make your end effector do something. And a lot of robotics control revolves around coming up with algorithms to come up with how do I position these joints and maybe move these wheels in order to get my end effector to a specific world fixed location, right? Because I've identified, there's this object I want to manipulate in this world fixed location, right? Okay. All right, we can move on. All right, we're going to talk a bit about commonly used controllers and algorithms we have and that we do. Let's talk about the most basic system, or very basic system, our air conditioning. Our air conditioning, when this room gets too hot, our air conditioner turns on for some reason, right? What it's doing is it's looking at the feedback data of this room, what the temperature of this room is, and at some threshold value, it's going to decide to turn the cold on to make it cooler. And in the winter, when the room gets too cold, it decides to turn the heat on because, well, because you said it to. And but it looks at this temperature, and it will turn on. This kind of control is probably the simplest and basic level. The name of it is, this is a textbook term, guys. Horrible. You can find that in textbooks. Bang bang control. Basically says if my value is higher than I need it to be, lower it. If my value is by a fixed amount, because the air conditioner you can't really modulate, it's not really able to output a certain amount of cold air or something like that. It's stupid. It's only able to just cool or heat or nothing. The next level of control, which people, this can be very complicated or very simple, and it all falls under the same category of fuzzy logic. Most of you, if you program for, say, Robotathon or something, and we didn't tell you how to do anything, you resort to something along the lines of fuzzy logic. Most of you here have made something like a line following robot or wall following robot, better yet, at some point here. I'm going to put my wall following robot on the floor here, and if I read a value greater than 700 on the sensor, turn right, or set my motor powers to this. If it's between 700 and 600, turn it this amount. If it's between 600 and 500, turn it this amount. Something like that, right? Fuzzy logic, we're specifying different depths of where it can be, and we basically pre-programmed and tuned these values that we're going to output. It can be a lot more complicated than that, although this kind of control is, one, difficult to tune because there's so many different things you can tune about it. And yeah. It is, however, fairly simple and does work, and some things do use it. I can't think of a better example than the line following robots that people tend to make for robot line kind of things. Okay, so the major topic that in this section that I'm supposed to cover is PID. What should my example be? I don't have a good. Okay, so while we were downstairs earlier for Region 5, we were programming. Chris, is Chris sitting here?
He's still
Okay, so Chris is downstairs programming the Region 5 robot, and right now he's trying to get it to follow the wall using the LiDAR, right? There's two values which he's balancing. I'm only going to balance one here, right? I'm not going to label this axis. Let's say I am the Region 5 robot and I want to follow this wall very smoothly and nicely, right? I'm going to say I want to follow it within 10 centimeters. This actually is going to be centimeters for some reason. All right, 10 centimeters. I'm going to start the robot out somewhere about 15 centimeters away. Here. Now, as time goes on, I want to try to move my 15 as close to this 10 as possible and maintain it and be beautiful. Ideally, in an ideal world, if you're playing, like, say, if you're making video games or whatever, you can actually control the world where I can just use this and sit there. Unfortunately, in the real world, we can't do this. And what we use for this kind of system would be along the lines of PID. PID says that I'm going to try to abstract away my system, whatever it may be, as a linear system. More so as, well, or as a differential equation, however you want to call it. So let's say I am 5 meters apart, right? Or 5 centimeters away from my target. This yields this number of, that we have 5 centimeters of error. We can move proportionally, which is the P on PID, to this 5 centimeters of error, whereas we say we're going to output more motor power in a certain way if, as our error, our difference in our desired and our actual or red data point is, how big that number is. And so what P control will look like, using only proportional, right, would do something like this. Basically, the slope of this line is equal to, so the derivative of this line is equal to my error, how far my red is away from my green. And this is how typically the system will look like if I have a P term. We add in typically a D term in PID control to dampen the system in a way so that we can achieve a line that looks something closer to that, where we land on it and it knows to slow down because the difference in our error is getting closer. This is a really hard topic to explain. The last of which is an integral term. So even with the D term, you're still going to bounce along this line a little tiny bit because there's this granularity happening in your actuator that you can't actually achieve this perfect system unless you add this I term, right? As I bounce along the wall, right, I can take the integral of my error, which if I have a whole lot of error, say, let's say, I have to change this a little. The Region 5 robot is on a hill. There's gravity happening. And so no matter how hard it tries, right, it needs to actually exert a little extra motor power in order for it to get on the line, because it's going to sit a little off the line, and it needs this error term here to drive it up against the hill so that it's still maintaining position. This can be corrected by an integral term. An integral term says, okay, well, I've accumulated error for a while now, and it will increase. It will accumulate, and over time, if I had error for long enough, it should generate enough power in your function to push it onto where your desired should be. The general equation for a PID controller, right, will look something like. By the way, this is PID on an error of your system, which later on I'll move into other things you can kind of add to this. So we often use the term, the output of my PID controller, which I'm probably going to output to my motors in this situation, is going to be my P gain. We use this term gain commonly. It's just often a tuned constant that you put in front of your controller. There's a bunch of little nuances in actually writing this in terms of software. There's a lot of code examples online and or in various places in our Git repo, because we've written PID controllers all over the place. For further, I guess these aren't really issues you hit unless you're actually programming it and you see what's happening. Not something that's easily explained in front of the whiteboard. What else? Okay, so the last one, I'm broadly categorizing everything more advanced than this as model-based control. So apparently there was a guest speaker on Tuesday, I missed it, and this guy stood in front of the room and kind of talked and wrote equations, and I think no one really understood him. I'm going to spend 30 seconds to explain what he was actually talking about, probably, at a lower level. Model-based control basically says, I know what my robot is, right? I know the mass of R2-D2, I know the diameter of the wheels, I know the friction between the contact surfaces, I know everything, and I know physics. I can solve exactly what motor power I need to output to my motors to do exactly what I want it to do, theoretically. It doesn't work perfectly in real life, right? But many attempts at it have many people have gotten very close to basically ideal control of your machine because you know so much about it and the world that it's interacting with. This is, all right, I'll move on to, yeah, okay, so what people actually came here to listen to about was RAS engineering. what is RAS? RAS, well, RAS stands for Robotic Operating System. It was written by the engineers at Willis Garage. Rest in peace, they're gone now. Currently maintained by the Open Source Robotics Foundation, which a bunch of people from Willis Garage went to work at. It was built for the PR2, Personal Robot 2, which is a robot they've made. And so a lot of the packages in there work for the PR2 and whatever other group actually used the RAS and uploaded their code. So a lot of what you see in RAS, don't expect it to work perfectly for your system because people made it for their robots and not yours. But still, it has a lot of what you need, usually, and it's open source, so hey, if you want to contribute, it's awesome. RAS has a core, right? There's a few pieces of it that is the center of RAS. Wait, am I going too fast? Okay, whatever. So RAS has, so RAS is for Linux, Ubuntu, usually you can install on other systems. They're trying to make it cross-platform, work on Windows and stuff, but not quite there yet. You can go online to ras.org and download it and look at their tutorials and follow it. Here's the stuff that you'll probably won't read about it, but it's probably really nice to know in order for you to actually get what's happening inside RAS. RAS has a core. This consists of the master, a horrible marker. The master. What the master does is it makes everything on your system talk to each other. Whenever you establish a node on your system, I'll go over what that means later, a node in your system, what it needs to do is it needs to ask the master for everything that it needs to know about the rest of the system. The core also has on it the parameter server, the parameter server is just a cache of all the parameters that you've set into the system. So as I write programs for RAS, I'm going to have a bunch of parameters probably because I'm not going to know everything about the use case of my program. A lot of what has been written for Region 5, I usually don't follow this, but it's actually good practice, right? If you go online and look at what code other people have written, they often have somewhere between 200 to 500 parameters in their nodes. And they're good because if someone wants to use that code for something not the thing you built, and they can do it, they can make it work for theirs by changing your parameters, they don't have to actually change any code to make it work. What else is in the core? Parameter server, master. I think that's it. That's mostly it. Well, at least this is an important part of your core. So when you type RAS core, this is what you're actually starting up. You also have RAS out, right? Whatever. The two main, there's a few concepts that are RAS specific. This is not having to do with robotics or anything really. This is RAS. A node is a program. Or more specifically, a process. Why use RAS in the first place, right? It's so that you can write a bunch of programs that a bunch of people, different people wrote, and they all can talk to each other and communicate data and run different algorithms, a bunch of stuff. And RAS is there to sanction the cross node or program communication. The two in-system forms of communication possible between nodes are topics and services. A topic can be looked at as a data bulletin, right? You have this, it's a broadcast and subscribe system where if, as a node, I can broadcast to a topic, post on this bulletin, this message, and as a node, I can also read from specific bulletins or be updated whenever something new happens on that bulletin. And so topics are composed of what RAS will call messages. A message is just a data structure, a struct, a class, or whatever you want to look at it as, a struct. And that you pass around between nodes so that they have data that they can communicate with. A service is the equivalent of a function call between nodes. So node A can call a function in node B if it's exposed as a service. This is the general structure of what's actually happening in RAS. There's a lot of intricacies that I can't really cover in this short lecture about it. The best thing I can probably do is give you a bunch of things that you can Google later. Depending on what you need for your system, right? A lesson that you should probably take from this lecture, I'd like for you to take from this lecture, is that a quote. Hold on, I want to try to get this right. A fool learns from his mistakes while the wise man learns from the mistakes of others. Often in RAS, what happens is that people will try to rewrite or have some problem that they need to solve, and their first instinct is, I'm going to write the code myself. That's not bad for a learning experience, but at certain points you want to get things done, you want to get it done faster, and at some point you'll probably learn that I'd rather not bother doing it myself. I'd just use the thing that works already. And so, libraries. One of the greatest things about RAS is that hundreds of people have contributed to it. There are plenty of packages that you can install and download and run, and they work right away. And RAS pretty much says that, well, we kind of know that we've tested enough to say that it works. And there's ones that it supports and ones that it doesn't really. Trying to think of important packages to go over. Just start listening.
UCL?
VCL.
Blue marker.
He's going to start listening to ones that he uses a lot. PCL, KDL, use KDL a lot.
KDL, OpenCV. Do you want to count TF as its own sort of thing?
Any package.
Okay.
Any stack, actually. TF.
Various drivers. Various drivers.
Yeah. What else? I'm going to start actually listing what these actually mean.
Arbos.
Yeah. So the PCL is the point cloud library. What it does is it's a huge library for processing point clouds in very different ways. Point clouds are what's generated from many different kinds of sensors, right? Stereo vision. If you have two cameras that are looking at the difference between the two cameras looking at the same thing, to get depth, you're going to end up getting a point cloud from that. A connect gives you a depth map, which can be also processed as a point cloud. If we have our, we'll also get a point cloud. It also does 2D point clouds, right?
I think it doesn't explicitly process 2D, but you can just set one of the values all to 0 or something.
Okay. Well, mostly 3D point clouds, but yeah. KDL is the kinematics dynamics library. It contains basic solvers, generic solvers for I erased R2D2. For chains of joints and links. For example, a common problem in robotics is the problem of inverse kinematics, where I have a series of joints and links, and I want to move it to a specific Cartesian space, say here. Where do I move each of my joints to get my arm here? This is actually quite a hard problem. It's an NP hard problem, right? I think.
You can get a closed form solution for some.
Assuming no closed form solution
or
something, right? It's yeah, it's an NP hard problem, and so there's no really good way to do it, but this library has one solution. It works for certain cases, right? It also does have recursive uniloader in there, right?
For single chain.
For single chain, which is the problem of inverse dynamics. If I want to apply one force, one Newton of force in that direction, what do I need to output? Well, what kind of forces do I need to output on my joints to output that 1 Newton, right? Those are the inverse calculations, which are a lot more complicated than the forward ones. And of course, it also does the forward ones, which are much easier. Given that this joint is here, this joint is here, this joint is here, where does my end effector tool frame end up in space? Same for the dynamics version of that. Given these forces along my joints, what's the force at my end effector? What else does KDL do? Is that about it?
Pretty much.
And pretty much. It also handles your models and stuff. You can give models and those parse it and stuff. OpenCV is also made by Willow's Garage. Same people who made RAS. It's the computer vision library. It has every computer vision algorithm, I think, that has been published ever in some way. So I can't even begin to list what it has, actually. Computer vision is, you have a camera and you're processing the data from your camera or something like that. Although RAS has a tendency to TF and URDF. TF talks about transform. Earlier I talked a lot about frames. TF is the package in RAS for your robot to maintain an account of all of its frames that it's aware of. URDF is an associated package which takes a model of your robot. So if I have a CAD of a robot, a computer-aided design of some kind of model of my robot already made, I can translate that to the URDF format, which RAS uses, and it will. And what you'll have is there's nodes that you can run that will announce to your they'll broadcast to your TF where my frames are, well, where your fixed frames are, or given that and the current joint locations, where what the current state of the body is. RAS also contains drivers for anything anyone commonly uses for that, mostly USB kind of devices or Ethernet devices that you'll plug into a computer that'll be running RAS. Gazebo is actually one of the key features of RAS. Gazebo is a simulator. Let's say I modeled out a robot, right? All I need to do is run this URDF thing and then run Gazebo, and hey, I have my robot in the world with very little. Well, to control it now, there's additional code, but actually, there's not a whole lot to Gazebo. Gazebo is interfaced by a bunch of service calls, and you can, in your RAS system, control your simulation robot in this graphical simulator. RViz and RQT together. Okay, so before RQT was RX, which was just plot and graph, right? I think.
And console.
Oh, plot, graph, and console. Yeah, RX, RViz, RQT. Depending on what distribution of RAS you're using, Fruite or older, you only have RX, and then Groovy and Ford, you have RQT instead. RViz is the visualizer for your robot. If you publish topics of the standard data types they provide in RAS, RViz will most likely be able to visualize it for you. For example, if I publish a point cloud in the standard point cloud message that RAS wants you to use, all you need to do is launch RViz and say, look at my point cloud, and hey, there's your point cloud. You have this nice GUI to look at your point cloud in real time, or in simulation, or in any way. This is the same for your model, your everything. RViz looks at everything. I can't think of everything. RQT is the other wrapper GUI around this. RQT actually contains RViz now. RQT in it has your basic GUI functionalities such as plotting out data points. If I have a topic publishing a single data point, I can run RQT, and it has I can look at a plot of this data over time. It has access to the console, which when you write RAS nodes, the convention that they want is that you publish, instead of using like printf, you RAS log. You use RAS's logging system, and that will go to a console. And so if you publish any kind of errors, you get to view it in a console that's basically the same as if you're, say, debugging code, you compile, and then you have your compile errors. You look at it in kind of that format. That's our the console. What's the third one in RX? Yeah, graph. RX graph, which is an RQT now, looks at your entire system. So the net of nodes and connections between nodes. So and this is used to debug, say I have 500 nodes and there's missing connections somewhere. I want to find out where it is. RQT has like 50 or so plugins by now that are kind of standard and you can download and use. People have made, it's basically a collection of GUI components you can use with RAS. And they all interface in the standard format. Bagging. RAS sanctions the ability to bag data, meaning record it and then play it back, which can be important in that you can run your robot and then record a certain set of data and run it over and over again, where you change as you change your algorithm to see how it affects it.
Action lib.
I don't remember. Action lib was in the same stack as plugins and nodelets. I guess all of them. Okay, so. There's a few higher level interfaces that you can use in RAS. ActionLib allows you to use actions, which is one step under services, essentially. The problem with the services is a function call, meaning you give it parameters, you wait for it to do its thing, and you get your return value or values. ActionLib sanctions for you to give it a command, let it return immediately without having to do this thing. It will update you with its progress as it goes, and then when it's finally done, it'll tell you it's done. This is better in the sense that it's non-blocking, and you get this feedback data in between as it happens. Right? The example I think they give in ActionLib is like do dishes or something like that, as opposed to what the service again? Never mind.
Add to integers or something? Add to integers?
Yeah, the service example is add to integers, which is something immediate. Plugins. I don't know a whole lot about plugins actually. So a lot of different programs in RAS, for example, RViz runs off of plugins, RQT runs off of plugins. Basically, you can it sanctions code that will run in some other environment under some other environment that communicates directly with it, and that increases functionality for it. Nodelets is a way to, rather than writing a node, which has its own process. Oh man, okay. I don't want to have to explain the difference between a process and a thread, but nodelets rather run under different threads within the same process. This allows for various forms of communication between nodelets that are a lot less overhead than topics and services. Topics and services have to talk to each other by opening up TCP or UDP pipes between them, and this causes a lot of operating system overhead underneath. A nodelet, however, will allow you to talk between different nodelets. I keep wanting to say nodes for nodelets, because the code difference between a nodelet and a node, assuming you're writing in C++, is trivial. Nodelets only work in C++ also. Basically, you're cutting out a lot of data overhead and talking between different nodes. This is used, a use case example of a nodelet is I have a bunch of nodes that do something to an image, right? Like IGBC last year, right? IGBC last year, we had a node that took in an image, that read an image from your camera. Then there was a node to, I don't know, like run canny edge detection on it or something. And then another node to run huff lines on it or something. And another node to ray tracing, etc. And between each of these nodes, what RAS is going to have to do, because they're nodes, different processes, it's going to have to serialize the data and then send it over a TCP pipe and deserialize it on the other end. And this leads to a whole lot of overhead. Rather, you can have each of these nodes be nodelets, and what they can do is pass a single pointer between each of them, and they can just look at the same memory, making it much faster. Any questions? Okay.
Can you talk about some of the stuff that you've done with RAS?
So I learned RAS originally doing IGBC with RAS. That was last year. And we sucked at it. Well, not at IGBC, but at RAS. It was very dirty. And then Josh comes in and tells us that we're doing it wrong. And then right now I'm working at Track Labs where we use RAS on the Atlas robot system, and the system is much more complicated than IGBCs, and so now I know all this stuff, right? Does that answer your question, Robbie? Okay. Was there anything you wanted to expand on? Okay.
Do you know of any other helpful sources to learn ROS aside from the website?
There are other tutorials in various places online, which you can probably find by Googling.
But nothing centralized.
Ross has a Stack Overflow kind of thing. Yeah, there's a robotics stack. So if you're looking for help on robotics concepts, the robotics stack is Exchange. ROS specific, people have mostly addressed a lot of the issues. So, I mean, well, what specifically were you thinking of?
Well, I just kind of want to understand the structure of ROS a little better, and also a bunch of specific stuff towards Mercury that we have to do. But
Okay. You're free to ask us questions whenever we're around. It's really hard to just because there's so much of it, and right now I don't know what's pertinent, really. The purpose of this was to try to make you a lot of trouble people have is that you know how to Google for things, but then sometimes you stare at that empty bar and don't know what to type into it, and this is what you should probably type into it to kind of help you out. Tools so that you don't need to know, don't look up everything because you want to learn it or anything, I would say, because there's a lot of stuff. But if you ever need something, ask the internet. This is what you should ask for those specific topics. Sorry, I couldn't actually answer your question. Better than, talk to Robbie knows everything. Anything else?
Yeah, is there a way to set up a GUI for us?
So you can set up your own GUI. RQT is the GUI that comes with it. What do you mean set up a GUI? What are you thinking of exactly?
I don't know. I just installed ROS today, and I have no idea what to do with it.
So the biggest hurdle with ROS right now is, especially because they're trying to move to Windows, is that it doesn't actually have a real good GUI for controlling ROS underneath it. So no, the answer is no. There is no GUI for ROS. Everything is command line, basically. To control things at a slightly higher level than what nodes to run it and stuff is RQT is the GUI. Other than that, depending on what you're programming in, and you're trying to make a GUI for yourself, just make a GUI in whatever you're programming in. For example, if you're using Python, make it in tkinker or Pygame. C++ has Qt. It's kind of old. JavaScript. Robbie made her GUI in JavaScript, and Chris's GUI is also in JavaScript, right?
But RViz is a really great tool for visualizing just everything.
Yeah. RViz and RQT has everything you could probably think of right away.
Not a lot of interaction, I don't know, just basic visualization stuff.
So RViz supports also interactive markers, whereas you can move something in your 3D world. The same way you'd probably move something in a CAD model or something, right? This little marker. And you can send that as messages. It can control things if need be. So it is potentially interactive. There's actually an interact button at the top. More questions? Possibly? Would you like for me to dismiss you? I'm not holding you hostage. You can leave if I'm boring. well, if you have any come up with any better questions in the future or things that you want to know about, because yeah, there's plenty of people to ask. I'm not around all the time, but Robbie's around all the time, so ask Robbie, basically. and if he doesn't know, he'll ask me. Or Josh. Josh will be here forever. Yeah, I hear Josh doesn't hang out at the bunker very much anymore. Or, I mean, not to the extent he hung out in the trailer back in the day. Probably because it's out of the way and you can't continue now. And he's aggressive.
All right, well, thanks a lot for doing the tech talk.
Thank you, Robbie.
I hope that was really relevant to people doing Mercury and Region 5, at least for the things that you could do if you're not already doing or things that you don't yet understand. So, it's a big world.